What I plan to do today is really sort of follow on from a webinar that we gave in the summer. My colleague Matt gave this, and it's one of the ones that you can find, as Catherine said, on our website in the webinar section, which was all about approaches for multi-parameter optimization. What I plan to do today is really build upon that. I'm going to start off just saying a few words to set the scene around the particular approach to MPO that we use at Optibrium within Stardrop. But what I'm going to focus on today is more about how we choose the most appropriate criteria to put into our scoring profiles, and then how we can think about analysing the impact of the choices we've made as we've set up those scoring profiles to the decisions that we're going to make as a result. I'm going to give a sort of an overview of how different approaches work within that, but I'm then going to dive into Stardrop to show you it in action. I'm particularly going to focus then on the whole process of building a scoring profile. So after a demo, I'll wrap up with one or two conclusions and then come to the Q&A. So as Catherine said, if, as I'm talking today, you think of questions, please jot them down, and I'm very happy to address them when we get to the end. So to set the scene, well, it's really MPO is drug discovery. What we're doing with drug discovery is in itself an MPO challenge. We're trying to identify compounds that have an optimal balance of properties. It's rather cartoonified in the diagram up to the top right here, where I've sort of pointed out a space within sort of a region within potency space where we perhaps find a hit or a lead. But of course, finding those compounds is a great starting point, but to develop a successful drug, we need to find the region of that potency space where we can also achieve the right balance of a number of other critical properties, whether that's safety, stability, solubility, absorption, so on. And it's that sweet spot where we have the potential to find our drug. And of course, what we want to be able to do is identify as quickly as possible the situations when this kind of balance just isn't going to be achievable. And again, rather simplified down in the bottom right there, where we perhaps do find some potent compounds in the region of chemistry space where we can find potency, but if it doesn't overlap with regions of space where we get all the other necessary characteristics, we're not going to be able to find a successful drug. And of course, we want to do this as quickly and efficiently as possible. But not just that, we want to do so with an understanding of the confidence we can have in making that decision. Pushing a compound forward or stopping a project, these are big calls. And we're often working with uncertain data, whether that's experimental error in our data, whether that's statistical error behind our models. So it's really important that we are able to think about the confidence we're having in our decisions, in particular, so that we avoid missed opportunities. We wouldn't want to be discarding compounds simply on the basis of uncertain data. So I'm going to assert that there are a few requirements that we want to meet for MPO and drug discovery. One of those is that whatever approach we use needs to be interpretable. We need to be able to understand the priorities that come out of our approach to MPO, and understand what these mean in terms of how we might want to then further improve our compound's chances of success. Our approach always needs to be flexible. We all work on different therapeutic objectives. And even within a project, the criteria we want to use may well need to evolve over the course of the project as we learn more. So we need that flexibility, and that really goes hand in hand with the weighting that we need to be able to apply to the different criteria within our MPO profiles to account for the relative importance of the different properties that we're using to assess our compounds. And then, of course, finally, we need our approach to be able to allow for the uncertainty in the data, so we can take experimental or statistical error into account to avoid missed opportunities. So the approach that we use for this is called probabilistic scoring. And within this, we can define a profile of the properties that are important to us. I've got an example profile showing here with just 5 properties in it. So this is a fairly simple profile, but for each of these properties, I've defined different desired values or ranges that I would like to be in, which essentially in combination would result in a successful compound. Alongside this, I also have the relative importances of these properties. So in this case, I'm saying that the potency is pretty critical to success, whereas I'd be willing to trade off the Hurg affinity being a little bit on the high side if it meant that I could get the other properties correct. So of course, every profile needs to be tailored to your own therapeutic objectives. But it's this combination of the desired value or the function that we determine, in combination with the importance, that really is essentially a desirability function. This is what we're looking for. We want to be up here, but we're willing to start. We're going to need to start penalizing compounds as they get further and further away from that sweet spot. And so within probabilistic scoring, we pull together our property data, whatever its source, the criteria for success that we defined, which includes those relative importances, and also the uncertainties in the data, again, whether that's experimental or statistical. And it's this combination that we pull together to generate the score being a likelihood of success, given everything that we know and what we're looking for. Of course, we fed in a lot of uncertain data as well. So there's uncertainty around our scores too. We can generate a confidence in our score, which we want to use when we're thinking about how we might prioritize or triage our compounds as a result. So as an example of some scored compounds, I have down here a very small data set. I've got 34 compounds that I've scored. And this chart that we've created is called a snake plot, where we have aligned the compounds along the x-axis from the best score to the worst. And we can see the score on the y-axis. Importantly, within a snake plot, we always want to see the error bars. These show us the confidence that we can have in the overall score for each compound. Now, there will always be a top scoring compound, but what this is showing us is that the data we've got available at the moment don't separate any of these top few compounds with any significance whatsoever. On the other hand, in terms of a prioritization and a triage exercise, I could say with confidence that the bottom 50% could be rejected. These are significantly less likely to be successful than the top compound. Of course, that leaves a gray region in the middle. So these are the compounds for which we don't have good enough data to distinguish them with confidence from the top scoring compounds or from those that we're going to reject. What you might say is, well, that's unfortunate. I want some clear-cut decisions, but really this is reflecting the reality of the data available. And what we need to do is sample these compounds and generate some higher quality data so we then know with more confidence whether to promote them or to relegate them. So it's all well and good having an approach that we can use, but how do we choose the most appropriate criteria? So what we want to be able to do is tailor a profile to our needs, and I'm going to lay out a few objectives for this that we're going to aim towards. One of those is that I want to be able to use my existing data to find new scoring profiles that are going to help me identify compounds that have an improved chance of success. Now, you can define what success means, and that could be based on really any kind of drug discovery objective, whether it's earlier stage or later stage. The whole idea is that we develop a profile that we can then apply prospectively to help find or to prioritize new compounds. And to do this, what we need to do is identify the most important data that enables us to distinguish between successful and unsuccessful compounds. And we can do this on the basis of any data, whether that's experimental or predicted. Ideally, of course, data that we're going to have available for our prospective compounds later on. And of course, it perhaps goes without saying that we're going to be exploring data multiparametrically. We want to be able to consider the properties simultaneously, not individually, because that's how we want to be able to apply them. But in doing so, we need to make sure that we avoid overcounting of any correlated factors. And then really going back to the criteria I specified for MPO in the first place, we want to make sure that what comes out of this is something that is interpretable and modifiable. We don't want any kind of black box. What we'd ideally like is an approach we can use to find tailored profiles that we as experts can make sure make sense to us. Ideally, do it in a way that is sort of synergistic between the power of the computer to find the rules and you as the experts to then make sure they're tailored to what you understand about the project. So what is a rule? I've used that term a couple of times, but really a rule is a set of property criteria that in combination can help us to identify good compounds, where we're defining what good means. I've got a couple of examples here. The first is the list of 4 different characteristics that I've pulled together, a sort of a range of molecular weight, a log P, a ligand efficiency. And of course, I'm sure you're all familiar with something like Lipinski's rule of 5. But that, even though I've got a very simple rule at the top there in terms of log P, LE, molecular weight, ppb category, this is really equivalent. It's a simpler version of, but equivalent to a scoring profile that I was just describing. Another way to think about a rule is that it's a box in multi-dimensional property space which contains significantly more good compounds than bad compounds. So in this case, and actually for all of my examples, I'm going to stick to 2 dimensions for showing you how it works. But of course, what we're really doing when we're building rules is looking at this in many more dimensions. But it's very hard to draw hypercubes and very hard to convey the principles of the approach that's being used. So I'm sticking to 2 dimensions for this. And for this example, I've got property X and property Y. And within that, I've sort of plotted all of my compounds. And in the key, we can see that I've got my good compounds colored blue circles. My bad compounds, are orange triangles. And across that space, there's probably a few more bad compounds than good, but there's a distribution across it. But what you can see is I've got a box in that space where there is a much greater proportion of good compounds to bad. It's about 3 to 1 compared to the rest of the space. So what you might think is, well, if I had a new compound and I could drop it into this space anywhere, if it fell somewhere within that box, I'd have more confidence that it's going to be a good compound than a bad compound, just because of the enrichment within that region of the space. And that region, of course, is, again, equivalent to a scoring profile, the size of that box being defining that function that we're looking for in terms of property X and property Y. So the method that we use is called rule induction. And this is all about trying to find those regions in property space with a higher chance of success. So what I thought I'd do on this slide is sort of show how rule induction works in terms of finding those rules. So it starts off by creating a rule or a box which encompasses all the points in the space. And then what it looks to do is remove one face at a time in such a way that you get enrichment of this region that's left. So again, I'm doing this in 2 dimensions, but if you can imagine it being done in many more dimensions, we're looking for the dimension where I can remove a bit of one of the faces in order to give myself a slightly smaller volume within which I now have an enriched set of good versus bad compounds. So in this case, we could sort of peel off this region to the right-hand side. We can see the region I've peeled off is all full it is totally full of bad compounds, meaning that the region left to the inside of that now has a greater proportion of good to bad by default. And of course, we can do this successively. I might remove this face down here, again, only ever moving 1 dimension at a time, and successively peel away different faces of the region so that we're getting a smaller and smaller box left within, where we're always looking to make sure that we're increasing the enrichment as we do so. And the box gets smaller and smaller until we get down to a point where removing any more face from that would decrease the enrichment. We don't want to go any further. Now, once we reach this point, what we want to do is let the algorithm flex itself a little bit, flex the other way, because this is quite a greedy algorithm for getting rid of areas of space. But of course, we may find that having moved ourselves down to the smallest available region, by pushing out in other dimensions, we can now bring in a few compounds that we'd otherwise excluded from the space. So we just let it, as I say, flex its muscles a little bit to see if it can grow out in any dimensions, in this case, in 2 dimensions that allow us to increase the enrichment by bringing a few more compounds in that were previously discarded. Having done this, we now have our first rule, our first box within the space. And so what we do is remove all the compounds that fall into that space, into that box, from our training set, and we start again with what's left. And again, we draw a box around the complete space and keep whittling it down until we find the next rule. So we may well find this rule next, and having been through this 2 or 3 times, we might end up with these 3 rules where we've got regions of the space where there are significantly more good compounds than bad compounds. Now, while we're doing this, we need to think about some criteria for judging the quality of the boxes that we're coming up with. So one of those is thinking about the average objective value in the box. So this is something we report as the percentage increase over the objective value for the full training set. We also want to think about the support of the box, so the proportion of the data sets that are covered by the box. So we report this as the percentage coverage, but this is all about making sure we get an appropriate trade-off between specificity and sensitivity. There's no value in us drawing a box which simply surrounds one single point in the space. So what we also report is a statistical significance of the box, so a p-value, and an odds ratio, so the probability of success inside the box versus the outside. So these are all things that I'll show you when I do a little demonstration that we keep an eye on as we're assessing the quality of the rules that we're coming up with. What we can also do, as well as finding the boxes, is think about the importance associated with the edges of the box, and also think about sort of soft boundaries around those. So the importance is something that we assess. The importance is really, if you look at this little chart here, the gap between the score for good compounds and the score for bad compounds. In this case, this hasn't got a very high importance because there isn't a big gap between these. For a very important property, we see this step function go right down to the bottom, where we'd be applying a much bigger penalty. But we work out the importance by looking at the ratio of the probability of a training compound meeting the criterion and achieving the objective to the probability of a training compound not meeting the criterion and achieving the objective. Apologies, that's quite a mouthful, but that ratio enables us to assess the importance of the particular criterion. We can also, as one of the options, we provide fit desirability functions to the box boundaries. So we can do a sensitivity analysis around the boundary of the box, around here, and through this data sampling, adjust the rule that we've got. So we've adjusted the importance here. We've also adjusted some of that boundary between what's good and what's bad. Again, applying sort of a softer boundary as we transition from the ideal down to compounds that criteria that we know are not ideal for our project. So I'm going to give a demonstration of building a profile, but I wanted to also touch on the fact that we want to be able to analyze the impact of the choices we've made. So whether we've built a profile using the kind of system I'm going to demonstrate in a minute, or whether we've put together a scoring profile by hand, it's really useful to be able to analyze the impact of what we've come up with. So what we want to be able to do is apply a sensitivity analysis that enables us to think about what impact changing a property criterion would have on the decisions we're going to make as a result of using it. Of course, we want to think about how large a change is necessary to have significant impact. Clearly, if we change all our criteria enough, we're expecting a significant impact. And what we're particularly interested in is when a very small change in one criteria can have a large impact. So we want to know which property criteria our compound priorities are most sensitive, and in particular, which of the criteria or importances associated with them will significantly change the order of our overall compound priorities if modified. So not so much thinking about will they have an impact upon the score itself, but if you think of using scoring to prioritize our compounds or rank our compounds, are there criteria which with a small change would dramatically change the way that we ordered our compounds when we prioritize them based on score? So small changes here, again, potentially highlight new avenues, or sensitivities, I should say, potentially highlight new avenues for exploration, and can at the very least make us aware of the potential for missed opportunities. There are a couple of considerations when we do this. One is that we need to be able to consider the statistical significance of any reordering that occurs. In particular, we want to take into consideration the uncertainties in the scores. And we're also particularly interested in changes to the higher ranked compounds. So if we had a data set of a few hundred compounds and we noticed that changing our criteria significantly reordered the bottom 20% of them, it wouldn't really make any decision, wouldn't have a major impact upon the decision we're making when we're thinking about prioritizing those compounds. If, on the other hand, the top 50 of those compounds ended up at the bottom, so we've got a completely different set of top compounds, then it's likely that that change is going to be something we really want to know about, because it's clearly a small change is having a dramatic impact, and our decision is going to be affected by that. So I talked about that sort of importance of uncertainty, and the way we use this, or the way we think about this, is based on using a modified Spearman's rank correlation to account for this. So I've got an example here where if I simply had 3 compounds that I'd scored, we can see their scores, which are quite different when plotted, but there's a big uncertainty around each of those scores. If I made a very small change to one of my criteria and ended up with these scores instead, in terms of the rank order of the compounds, well, it's flipped on its head. But given the uncertainty in the data, we wouldn't say that this is necessarily a significant change. On the other hand, if I had exactly the same scores, but they were a lot more confident this time, and a small change did the same, flipping them on their head, and I had the same level of confidence in each of these scores afterwards, we would say that this change is significant because it's much less likely to have occurred simply by chance. So just to give an example of this sort of in slides rather than live, I've got a profile here of 11 properties. You can see the top one of those is activity against 5-HT1A, where I've got sort of very high importance in terms of that activity. But I've also got solubility, absorption, log P, just a variety of ADME and phys-chem properties. And what I'm doing with a sensitivity analysis, thinking about the impact upon my data set. So we're not really doing a sensitivity analysis of the profile itself, but it's the profile when applied to the set of compounds that you are analyzing. So for my data set, I want to know which of these parameters are most sensitive. And so I can run an analysis and see for each of the criteria in the profile, how sensitive we are, or how sensitive the data set is in terms of the value or the criteria that have been specified, and also separately, how sensitive we are to the importances that have been set. What we'd like to know is what magnitude of change has a significant impact. So one of the things we can look at is the shape of the curves around our starting point. So at the bottom here, I've got a chart which shows a property shift value, which is starting at 0. So this is where our scoring profile is at the moment, and where this particular criteria is sitting. What we can see is as we adjust that criteria, either by decreasing or increasing it, the slope is very, very steep. So this is why this is flagged as a highly sensitive property. And of course, what we want to know is which of the compounds are most affected by this. So what we can do is take a look at the scores of our compounds and then compare them with new scores that we would see for those compounds as we make a change. So what I'm going to do is shift this property and then use that to see the effect on the scores. And then we can see why this is flagged as a particularly sensitive parameter. So as I shift very slightly up to the right here, although I've only moved sort of not even 0.2 of a log unit, we can see there's a number of compounds and a few compounds which previously had high scores, which are now significantly decreased. And as I move further up this way, you won't be surprised to see that as we move up this steep slope, more and more compounds are seeing a dramatic change in their scores. So this is why this is flagged as a highly sensitive parameter, because fairly small changes to it, less than a log unit still, are going to have a dramatic impact upon scores. If I pick a different aspect of this profile, so I look at the sensitivity towards the importance associated with the blood-brain barrier penetration we have in the profile, we see a very different shaped curve here. It's very, very flat around the point in the profile at which we're sitting to start with. And so if I perform the same exercise, as I move to the right of this point, up the gentle slope, we can see that there's only very minor changes occurring to the scores of the compounds. Indeed, I have to move a long way, even right to the far end, and even then, there are not dramatic changes really to any of the scores. And so this is why this is flagged as an insensitive parameter. So this is a very useful way that we can sort of sanity check that when we're using a scoring profile on the data, that the results on which we're basing our decisions are not particularly sensitive to any of the criteria we're using to make those decisions. It may not stop us using these criteria, but we can at least be aware of it if we see particular sensitivities highlighted. So I promised to show this in action. So what I'm going to do is switch out of my slides and I'm going to open up StarDrop. So for those of you that don't know StarDrop, StarDrop is our software for design, visualization, and analysis of small molecules. Within this, I'm going to be particularly focusing on StarDrop's functionality for scoring compounds, in particular for building scoring profiles for compounds. But if there's any aspects of this about which you'd like to know more, as Catherine said, we're very happy to do so. I'm very happy to give you an opportunity to find out. I have in StarDrop a dataset here on the right. This dataset actually comes from the paper by Travis Wager and his colleagues at Pfizer 10 or 15 years ago now, where they published what they called CNS MPO score, which was an approach they developed for using a small number of physicochemical properties to distinguish between drugs and candidates. So I should say CNS drugs and CNS candidates. So the properties they used were C-log-D, TPSA, C-log-P, pKa, molecular weight, and I've got all of those calculated in this dataset already. The dataset has 227 compounds. You can see I've got the drugs at the top of the set. We can see their names here. And then further down in the set, I have a number of candidates instead. So the idea of that was that the CNS MPO score, which I also have calculated in the set at the side here, compounds with the highest scores, ideally scores above 4, the drugs, and the candidates themselves were getting lower scores. So this was published a number of years ago as a way of being able to make this distinction on the basis of some simple properties. What I'd like to do today is use this data set and build a scoring profile based around these properties to distinguish between drugs and candidates, to see how we can do, see how well we can do in terms of coming up with a profile that can do this, instead of using CNS MPO score. So what I'm going to do is kick off the process of building a new profile. And what I'm going to tell this is that I'm going to be using a categorical objective. So in my data set, I have this column which is either drug or candidate, so it's categorical data. And I'm going to specify that I'm looking for a high outcome. Now, what that means in terms of my categories is the highest value of these things. So I get to order these. If I had multiple categories, I could use this to order them to say, well, which are the higher value ones, which are the lower ones. So I've ordered them, as it were, a numerical order. So 1, 2, 3, 4, 5. In this case, there's just 2 of them. So drug is the higher value in terms of these 2. So that's what it's going to try and use the profile to find. As part of this process, I can define how I want to split the set in terms of using a proportion of it to build the profile, and then keeping a proportion aside with which to validate the profile that's been generated. So in this case, I'm going to use the default split of 70-30. So 70% of the data will be used to build the profile. Then we'll see the results for the final 30%, which we kept sort of independent and separate until the end. And I'm going to generate that based on a random selection. And one of the last things I can do is specify the properties that go into this. So in this data set, I have the 6 physicochemical properties. I also have CNS MPO score in this data set. So I'm going to remove that. It would clearly be inappropriate if I were to use that in order to build a scoring profile. So I make sure that's not included. And I finish off by confirming the proportion of the data set that I want to make sure is covered by the rule I come up with. In this case, I'm going to stick with a default of 20%. And again, with only 2 categories, there really isn't any choice of a minimum desirable category. Drug is the only desirable category that I'm asking it to look for in this case. If I had more categories, I might choose 1 or 2 categories that are desirable versus the others. So it's really an opportunity to specify a threshold against which we want the profile to distinguish. So when I hit the finish button, I get the first rule. I'm going to open up this window. There's a lot going on, so I'll sort of walk through this. Most importantly, up on the right here, we can see the first rule that it's come up with, which is based upon a combination of molecular weight, pKa, and C log D. So I want a molecular weight less than 322, pKa less than about 9.7, and C log D less than about 3. And it thinks that's the first rule that we can find. We can see for that rule, we have a mean improvement in our training set of getting on for 40%. And importantly for the validation set, we can see that that is sort of above 50%. So a very nice mean improvement. We can see the p-value is nice and low and nice high odds ratio. So that's looking very promising. We can also see this nice profile coverage. I said it had to be greater than 20%. We're nicely more than that. So on the face of it, this looks like a promising rule. But I did talk earlier on about synergy between the computer and the experts. So what we can do within this is actually explore the rule to our heart's content. So these charts on the left-hand side give different slices through the rule. They pick 2 of the dimensions, and then they show those dimensions aspects of the rule with the blue lines that you can see on the chart, which are effectively showing the box in terms of that part of the space. Now, I may well look at this and think, well, actually, if I were to shift that just to the right, I could bring in a few more yellow points here. I should say yellow points down here are the most desirable ones. These are the drugs. Red are the undesirable ones. So if I move this around and bring in a few more yellow points, well, this rule might get better. The grey points we can see within the charts, these are the points which are excluded by the dimensions which aren't shown. In this case, the other dimension which isn't displayed. But if you had 4 or 5 of these different criteria, then there'd be more dimensions which are potentially excluding points from your chart. So I can play around with these boundaries if I'd like to try adjusting them. As I do so, the rule itself is changing. And at the same time, our assessment of how good the rule looks is also changing. What nearly always happens when I change the rule, I tend to decrease the mean improvement. And so we can see in this case that the mean improvement in the training set is now down to around 20% and 40%. So although I'm sort of playing around and having a go at this and seeing if I can make the rule better, what I may well want to do is reset it back to where it was. You can see in this case, although I've got these values looking better now, I'm now below the profile coverage thresholds that I would set myself. So at any point that I want to, I can reset back to the point that the rule that the computer found, but it allows me to sanity check the rule, particularly if there are criteria that appear here, and I think, well, that doesn't really make sense in the context of the rules, in the context of the project and my understanding of the underlying data. If I'm happy with the rule, and I'm going to say I am in this case, what I can then do is say, right, well, let's see if we can find another rule, in which case I'd hit the Find Next button. What this will do is set rule 1 in stone, because it's effectively removing all those compounds that meet that rule from the set, and then starting to build another rule for me. Now, if it can't find a rule, it'll tell me. In this case, it's come up with a second rule. This second rule is based purely upon the molecular weight. If we take a look at the mean improvement, we can see the mean improvement is nowhere near as high as it was for the first rule. We can also see that the the p-value is sort of not far off 0.05, so it's starting to become a lot less significant with lower odds ratio. So although we've got a much better profile coverage, this second rule is a lot less compelling. It's also adding quite a bit of complexity when we come to interpret this rule later on. So in this case, what I'd probably say is, well, it's not entirely exciting, second rule. I'm going to discard this and stick with what I came up with to start at the beginning. So I hit the discard button. That leaves me with my original rule. And assuming I'm happy with it, I can click the OK button. And now I have a new scoring profile in StarDrop. So I can use this scoring profile and run it. I can use this to generate scores for all of these compounds. Now, StarDrop is naturally suspicious of any data set where there is no uncertainty. But this is the original data set. There's no uncertainty associated with any of these different properties. So I'm simply going to confirm that that's OK. And it will now give me a score for every compound. The score is a value between 0 and 1, which tells me the likelihood of being successful, which in this case is likelihood of being a drug versus being a candidate. So what I'd like to see is some nice high scores for all my drugs and some much lower scores for all of my candidates. Now, rather than eyeball this to find out how I feel about it, what I'm going to do is use visualization and a particular chart called a receiver operating characteristic curve, because this enables me to take a look at how well I can use a numerical property in order to act as a classifier. So in this case, what I'm doing is using my score, which is in this property here, where I've said the desired result is drug, and I want it to be able to act as a classifier for what I've got in this set column here. What we can see on a receiver operating characteristic curve is the true positive rate against the false positive rate as we adjust the threshold we're using to make that determination. Now, in a perfect case, what we would like to see is a curve that goes right up, sort of following the axis and then along the top, because that would mean that we've got a perfect classifier. And we'd see an area under the curve of 1. Our area under the curve is about 0.68, 0.69. We can see this curve here, which is pretty good. It's nicely above this line here. So if you see a line that sort of follows this point, or sorry, if you follow this line somewhat, you get an AUC of about 0.5. What that means is you haven't really got anything that can classify one way or the other. So this is quite promising. What I'm going to do is compare this to CNS MPO. And so what I'm going to do is take a copy of the chart, but in this case, rather than plot my score as the classifier, instead, I'm going to use CNS MPO as my classifier, and we can see the equivalent curve for that. So what we can see here is that it's not as compelling. It's a bit noisier, but of course we've now got three more properties being used within this determination. We can see the AUC is about 0.61. So effectively what we've shown through the profile building process is that by using half the number of parameters, we can do a better job of distinguishing between the drugs and the candidates. Now, I'm sure some of you are thinking to yourselves, well, Odin, you've just used this data set in order to build the profile. It's a little unfair to use this to judge how well the profile's doing. And that is a very fair point. So I have another data set here. I close that chart for a second, which is a slightly different data set. It's to address that first point about not using the same data set for judging what we're doing. It's also sort of thinking about the fact that by the time we get to candidates, compounds are pretty highly optimized anyway. What's potentially a lot more useful is being able to make that determination between earlier stage compounds and drugs, because obviously we have to make a judgment call and then before we invest heavily in them to get them to the candidate stage. So this is a data set we've pulled out of Kemble, which has a number of different drugs. So none of these drugs are part of the original set. And then it also contains a number of lead compounds. Again, there's no overlap between this and the CNS MPO data set. But in this case, we've really got lead compounds and drugs, and we want to see how well we can use the CNS MPO score and the profile we came up with to distinguish between these. So if I go back to our chart of CNS MPO score, I can plot onto this second data set. So if I add this test data set to this, we can now see the curve associated with this test data set. We actually get a slightly better AUC for this, which is nice. So this is giving us some distinction between these lead compounds and the drugs on the basis of CNS MPO score. If I go back to our original chart, well, what I need to do is run the score on these compounds first. So use this scoring profile we came up with, generate a score on the basis of this. Again, we've got the suspicion from Stardrop in order to give us a score for each of these compounds. And then within our visualization, add this into the chart so that we can see how well we can do using the scoring profile to distinguish between drugs and leads. And we can see in this case, we do actually a much nicer job. So it's actually a very nice, very positive curve here that shows us the ability of this scoring profile to do exactly what we were looking for. Importantly here, it's got half the number of properties that CNS MPO score has. So we've managed to focus in on those properties that are most powerful when it comes to distinguishing between drugs and leads. So that was what I wanted to demonstrate in terms of putting it into action. I'm really just going to wrap up with one or two conclusions. The first is really just a broad statement about MPO, and hopefully a webinar in the summer and what I've touched on today really helped highlight how important MPO is for enabling us to select and design high quality compounds. It really is powerful for helping us target those compounds that have the highest chance of success, and for helping us to avoid missed opportunities, not being led astray by uncertainty in the data. I hope what I've demonstrated today is the importance of choosing the most effective criteria, really focusing on those properties that enable us to identify the best compounds. And also I've demonstrated how we can think about the impact of our choices. Our choices when we're setting up a scoring profile, we can consider how sensitive the results we're generating on the basis of using that profile are to the criteria that we've used. And of course, this is a data set by data set process that we always want to be able to keep in mind. I've got a number of references here that sort of touch on the different work behind what I've described today. But I'm going to hand over to Catherine now and say, very much appreciate your attention and for joining us today. And I'd be very happy to answer any questions that have come up.
Thanks so much, Ed. Yeah, we've had several questions come in. So I'll start off with how much historical data do I need to build a profile?
It's a nice question. It's a bit of a how long is a piece of string question, but it's very much along the lines of what data do I need to do some modeling. So the example I had in terms of CNS MPO was a couple of hundred compounds, and with a smallish number of parameters, we could see we could very effectively come up with a profile. The larger number of parameters you've got, the more data you may need in order to distinguish between them, but you don't need huge data sets. You don't need thousands of compounds in order to be able to come up with these profiles. But clearly, the more historical data you've got and higher quality of those data are, just like in any modeling exercise, the better chance you have of coming up with an effective profile.
That's great. Thank you very much. And I forgot to say a reminder, but it's on the screen. If you have any questions, just click that Q&A button and write them in. Okay, next question. Someone's asked, how will sensitivity analysis help me if I've already got a property profile?
So the key thing about sensitivity analysis or what I described was that really it's not so much about analyzing the profile, but the sets of compounds that you're using and the decisions you're making on those compounds using the profile. So you can think of it as a tool that you can apply really each time you're coming up with a new set of compounds that you're scoring and assessing, particularly if you're making decisions about pushing some of those compounds forward or triaging them, so rejecting some of them. So it's very much something to be used hand in hand. And every time you are using scoring, bear in mind that when you're making big decisions, just being aware of the sensitivity of your data sets to those criteria can be very, very helpful for avoiding missing opportunities.